So we're going to talk about some what are called simple gas laws. And these are laws, they just describe what happens, they don't explain why. We talked about kinetic molecular theory, that explains why gases behave the way they do. The gas laws just describe what they do. We can observe that the pressure of a gas sample depends in part on its volume. If you change the volume of the gas, you change its pressure. So if we keep the temperature constant and the amount of gas constant, what we observe is the pressure of the sample will increase if the volume decreases. So imagine a balloon, and if you put pressure on it, then it's going to get smaller, right? If you expand, if the volume gets larger, the pressure is lower. So there's an inverse relationship here. This is what's going on in a bicycle pump. It's also what's going on in your lungs when you're breathing. So here's a bicycle pump. It's got a one-way valve that allows air to come in, and the only way for the air to go out is through this hose into your tire. So when you lift up on the pump, it's basically a piston inside of a cylinder, and you are increasing the volume of the gas in here. That causes the pressure to decrease. The pressure outside then is greater than the pressure inside, and the air will go in here because it wants to equalize the pressure. When you press down on the plunger and decrease the volume of the gas, that increases its pressure, and now the gas is going to try to get out. If the pressure in your tire is lower than what's in here, the air will go into your tire. And this is also a one-way valve so that it can't come back in. So we see the inverse relationship. This relationship between pressure and volume was discovered by Robert Boyle back in the 1600s. So this is before electricity, before we knew what an atom was. He was doing experiments with gases. And Boyle's law assumes that the temperature remains the same and that you're not changing the amount of gas. So Boyle's law says that the volume of a gas and its pressure are inversely proportional. So that can be expressed this way, or more commonly like this. So this is Boyle's law, the equation. Pressure 1 times volume 1 is going to equal pressure 2 times volume 2. I will not test you on remembering Boyle's name or associating his name with pressure and volume. I think that's a waste of brain power. You could look that up if you needed it. I'm not going to test you on that. So this is the sort of experiment he did. This is a J-shaped tube that's open on one end and closed on the other. So there's a gas in here, could just be air, could be hydrogen, anything. And then there's mercury in the bottom of this curved part. This side is open to the atmosphere, and so the pressure here is going to be equal to the atmospheric pressure, and the pressure inside is going to be equal to the difference in the heights of these two columns of mercury. So just like with the barometer, we can measure the pressure here by taking out a ruler and measuring the difference in the heights of the column of mercury. And that would be measured in millimeters of mercury. If you add more mercury to this, the mercury here is pushing down, and it's going to press on the gas and increase the pressure of the gas and squeeze it. And so you can see that the volume went down, and H, which is the pressure here, is larger. So you can do experiments like this just by adding more and more mercury, measuring the volume, measuring the pressure by the difference in the heights there. And so this is the sort of data you could get. Here's the volume of the gas and the pressure. As the pressure increases, the volume decreases. So if you graph volume versus pressure, you get a curve, which is pretty and nice and everything, but lines are more useful. So if we graph volume versus 1 divided by the pressure, then we get a beautiful straight line. And that tells us that the volume is proportional to 1 over the pressure. Yes?
Will it be tested on the graph?
No. You will not be tested on the graphs. So kinetic molecular theory explains what Boyle observed. Here we have a container that's got a movable lid so we can change the volume of it, and we've got a pressure gauge on it so we can measure the pressure. Here we have a volume of 1 liter, and at that volume the pressure is 1 atmosphere. When we put a heavier weight on here and press the lid down so that the volume is cut in half, the pressure increases by a factor of 2. So the volume decreased by a factor of 2, the pressure increases by a factor of 2. Kinetic molecular theory explains how this happens. So here the pressure is based on the collisions that the gas is having with the walls of the container. If we cut the volume in half, same number of gas particles, same temperature, so their speed is the same, these gas particles are going to run into the walls more frequently, right? You think of putting a bunch of kindergartners in a room and then pulling a divider and cutting the room in half, and now you've got the kindergartners in half the space. And they're running around because they had cookies and cupcakes because it was somebody's birthday, right? So they're running around. When they're in a smaller space, they're going to run into each other and run into the walls more frequently. Does that make sense? I know it's a weird analogy, but you can picture kindergartners running around like little crazy people, right? They like to do that. They do. So more collisions here causes an increase in the pressure. So you change the volume of the gas, you change the pressure. So we need to learn how to do calculations with Boyle's law. Boyle's law has 4 different variables in it, 2 pressures and 2 volumes. So in a Boyle's law problem, you'll be given 3 and asked to find the 4th. So here's an example. A cylinder equipped with a movable piston has an applied pressure of 3.0 atmospheres and a volume of 5.0 liters. What is the volume of the cylinder if the pressure is decreased to 2.0 atmospheres? Now, from what we've talked about, we can predict, is it going to be larger or smaller? We're decreasing the pressure. So we expect that the volume's going to be larger. But let's do a calculation. So what I recommend, because there's lots of numbers and letters and things, is to make a table. So you read the question and then go through again, picking out the numbers. So we'll go along here. The first number we come to, 3 atmospheres. So I'm going to make a table here. And I'm going to call this row 1 and that row 2. And it's not initial and final because that really doesn't matter. It's just 1 and 2. And so whichever one I come to first, I'm going to call that 1. So the first number I come to is 3.0 atmospheres. Write the unit. An atmosphere is a unit of pressure. It also tells me this is a pressure. So I'm going to label that column P for pressure. Pressure of 3 atmospheres and volume of 5 liters. These 2 numbers, this volume and pressure, go together. Do you see that? Those are together. So I've got 5.0 liters, and that's a volume. Keep reading. What is the volume? Okay, that's the question. That's not a number. If the pressure is decreased to 2 atmospheres. So this is also a pressure, so I'm going to put it in the pressure column, but it goes in the second row. I should have 1 square that's left. It's not, well, 1 rectangle. That's what I'm asked to find. What is the volume? So this is, okay, that's not a V. This is the volume column. It's in liters. But... So this is V, and it's V under the second set of conditions, so I'm going to call it V2. Any questions? I'm just taking the numbers out and putting them in a table so I can organize them.
They're always going to be like that, like in that order, and always to find that same one.
Well, different questions will ask you to find different things. So in a Boyle's Law problem, you might need to find pressure 1 or pressure 2 or volume 2, but you fill these in and then label the one that's blank. That's why it's important to recognize that this and that, those two go together, and then there's another sentence. What is the volume if the pressure is decreased? So this is some change happening. So this is under a different set of conditions. So that would be separate. So we've got the table. Now we need Boyle's Law, which is right there at the top. P1 V1 equals P2 V2. This is a nice one because there aren't any fractions in it. So we want to rearrange this equation so that we get V2 equals something. So here's V2 over here. So I'm going to divide by P2 because I want to get V2 all by itself. If I do it to one side, I have to do it to the other side. So I'm just going to rewrite that down here at the bottom. V2 equals P1 V1 over P2. Be careful that you're copying them down correctly. It's really easy to transpose the numbers and stuff. So this is my equation, and I'm going to plug these values in with their units. So pressure 1, 3.0 atmospheres. Volume 1 is 5.0 liters. Pressure 2 is 2.0 atmospheres. So I've got all my numbers in. Then I want to look at the units before I do any calculating. And I see that atmospheres and atmospheres cancel each other out. That's encouraging. I'm left with a unit of liter, which is a unit of volume. And then I do the math. 3 times 5 divided by 2. I should have two significant figures. That's what my calculator gives me, 7.5, and the unit is liters. We predicted that the volume would go up when the pressure was reduced, and it did. Any questions? This is not the only way to do these sorts of problems. There's another way involving ratios and thinking about it, and if you want me to explain that one to you, I'll happily do it to you in private. I don't want to confuse everybody else. My experience is that even though many 3A students are not friends of algebra, using the equations is actually more straightforward for this than doing the other method. Boyle's Law explains some of the aspects of scuba diving. When you go underwater, in order for your lungs to expand, your lungs, the muscles in your chest expand your lungs, but if there's too much pressure on the outside, like when you're submerged far underwater, your chest muscles aren't strong enough to expand your lungs, and you would not be able to breathe. So a scuba diver will use pressurized air in a tank so that as you descend, because the water puts a lot of pressure on you. If you've ever gone to the bottom of the deep end of a swimming pool when you had a cold and your ears were plugged up, you know that. The pressure on your ears is like, oh man, that's uncomfortable. I'm going to go back up to the top. Every 10 meters you go down, the pressure from the water increases by an atmosphere. So at 20 meters below the surface of the water, the pressure being put on you from the water is 3 atmospheres. That's 3 times the pressure at the surface. In order for you to be able to breathe, the air in that tank also needs to be at 3 atmospheres. Otherwise, you're not going to be able to expand your lungs to breathe. So every 10 meters that you go down, you get an extra atmosphere of pressure. When you ascend from that depth where you're breathing 3 atmospheres of air, when you come up, it's important to not ascend too quickly and to be breathing in and out as you come up. Because if you were to take a breath here with a pressure of 3 atmospheres and hold your breath and ascend quickly, that would cause, at the very least, significant pain because of the pressure of 3 atmospheres without any support on the outside. Just 1 atmosphere. You'd have a 2 atmosphere pressure difference, and it's like overinflating a bicycle tire. It's kind of gross to even think about. I don't like this problem. For one of the first gas law problems, this involves far too much thinking. But here it is, we're going to do it anyway. So we read the problem first. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? Okay, fine. That probably didn't make a lot of sense. Let's just go through it and pull out the numbers and make a table, because that's what we do. So the first number we come to is 16 milliliters. That is pressure or volume?
Volume.
That's a volume. Okay, 16 milliliters of air at the surface where the pressure is 1 atmosphere. So that goes with that volume. So we'll call that condition 1, and this column will be pressure. So this gas, this air, has a volume of 16 milliliters at 1 atmosphere's pressure. Bunch of words. Next number, 7.5 milliliters. Well, that's another volume. This is row 2. So now in my little grid here, I have 3 numbers and a blank. And the question is, what is the pressure at this depth? Okay, so I've got a blank here for pressure. I'm going to call that pressure 2. We're going to answer the first question and not worry about the second question just yet. Okay. So I've got Boyle's law. P1, B1 equals P2, B2. This time I'm solving for P2. The process of rearranging the equation is the same. I want to divide by V2 because I want to get rid of that, move it to the other side. So P2 is equal to P1, V1 over V2. Then I take my numbers and I plug them in. Volume 1 is 16 milliliters. Pressure 1 is 1.0 atmospheres. Volume 2 is 7.5 milliliters. I check the units. Milliliters are canceling. Are we expecting that the pressure here is going to be greater or less than the pressure at the surface? It should be greater. Okay, so we've got 16 times 1 divided by 7.5. My calculator is showing me 2.133 repeating atmospheres. For significant figures, I should have 2, and so we're going to call this 2.1 atmospheres. That's the pressure at that depth. Any questions? This last part is what makes it challenging. If the pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? Well, how many atmospheres greater is the pressure here than it was at the surface? It's 1.1 atmospheres larger, right? It started out at 1.0 atmospheres, and it went to 2.1 atmospheres. The difference there is 1.1 atmosphere. The pressure increases 1 atmosphere for every 10 meters. So, yeah, the 11 meters. So 1.1, that's the increase. It increases 1 for every 10 meters. That's a conversion factor. 1 atmosphere for every 10 meters. So if I take the 1.1 atmospheres and I multiply by 10 meters per 1 atmosphere, I get 11 meters. That's how deep the snorkeler went with his syringe of air. Any questions? This understanding this last part is not super important. Getting to the 2.1 atmospheres, that's important.
So we're gonna have some of those on the exam?
I wouldn't ask you a question like that on an exam. No. It would stop here.